Alright guys, let's try to finish this off. So before the break, we looked at this hazard rate function. And what did this hazard rate function do? Well, given some random variable with some underlying distribution, we'd say that, okay, it's at least size t. And we think, well, it's not infinite in length or value. So there's some point where the random variable stops. So it's either finishes being processing, a bus arrives, if you're a part, it fails, things like that. And what this hazard rate function does is says, okay, well, if you made it to a time point t, the rate at which you're going to complete or have a hazard or a failure, etc., moving forward is going to be this rate, h of t. So you can think of 1 over h of t as the expected remaining time. So 1 over h of t, given that a job is at least 10 seconds, 1 over this function is going to be the expected remaining time for that particular random variable. So, I mean, depending on the underlying distribution, you might have, different patterns or observations you can make from this function, but there are two versions of this function that we're interested in. That's increasing hazard rates and decreasing hazard rates. So if you have an increasing hazard rate, that means h of t, so I'll just say this out loud again, and you can pause the video and fill it in your notes. IHR is increasing hazard rate, DHR is decreasing hazard rate. So the function h of t is increasing in t? No, it's non-decreasing. So why isn't it called non-decreasing hazard rates? Well, everyone hates saying non-decreasing and non-increasing. It just gets the idea across. So h of t is non-decreasing in t, and if it's DHR, decreasing hazard rate, that means it's non-increasing in t. And why would this be helpful for us? Well, remember what we were trying to do. We go back to the MG1Q and we're looking at service disciplines. And we're looking, well, okay, if a new job arrives and a job's being processed already, should I start processing the fresh job or should I continue processing the job that's already, in process? Well, if you know something about this function, that's going to tell you what you should do in general. For instance, if I have an increasing hazard rate, that means the expected remaining processing time for a job is actually decreasing. So that means if my underlying distribution is IHR, it's actually beneficial for me to continue processing the job that's already at the server. If it's DHR, I find myself in this position where the larger the job becomes, the larger I expect it to be. And we'll get back to that in just a moment. It's essentially what we call this heavy-tailed style of distribution. But anyways, if I've been processing a job for 10 seconds here, I actually begin to expect it to be much, much larger than 10 seconds, or much, much larger than the mean of the distribution. So if my underlying distribution is DHR, I actually, it's beneficial for me if I'm looking to minimize response time or have a lower response time to actually process fresh jobs rather than ones that have been served a little bit already or previously before. That's interesting. Might be a little bit counterintuitive, but basically, depending on what your distribution is here, is going to highly affect that choice of, well, should I do first come, first serve and just stick with jobs that are processing? Or should I do something preemptive, like preemptive last come, first serve, or random order of service preemptive, or something like least attained service, etc.? Well, that's going to depend on what the underlying distribution looks like in terms of this hazard rate function. Okay, well, let's look at some distributions. What about the uniform distribution? Is it IHR, DHR, both, neither? So can you be neither? Yeah, so you can definitely be neither. Basically any function with a PDF with like, certain peaks and valleys and stuff, if that was like a PDF, that would be neither, because there's parts where it does increase and parts where it does decrease. But we're going to be mainly interested in when it's like one or the other, and then we'll get back to the question is, can it be both? That should go against like your intuition, but we'll look at that as well. Well, what's the uniform distribution? So if I have some random variable that's uniform between 0 and 1, let's say, is that random variable IHR, DHR, neither, or both? Well, how are we going to determine that? We're going to derive the hazard rate function. So I'll try to do this off the top of my head. This is going to be the PDF of a uniform distribution is 1 divided by B minus A over 1 minus the CDF. Oh boy, what do we have here? Well, I think it's again over B minus A. Let me just check my notes real quick. I try to remember all this stuff and it's like, well, do I really need to remember it? It'd be nice if I could. So I think it's T minus A here. Do some simplifications, and I think, what do we find? 1 over, I should have looked at this as well, B minus T. And that's for T between 0 and 1. Otherwise, it doesn't really make sense. Okay, is this increasing hazard rate or decreasing hazard rate? Well, in order for it to be an increasing hazard rate, this has to be non-decreasing in T, meaning as T gets larger, we have to be non-decreasing. So what happens here? Well, it's between 0 and 1. So if T equals 0, this thing equals 1. If T equals 0.5, this thing equals 2. And I mean, your 4th year university students, you should be able to see that this function is increasing in T. As T gets larger, this thing begins to increase. Well, if it's increasing, that means it's non-decreasing, and therefore the uniform distribution is IHR. Increasing hazard rate. What does that mean? Well, if my jobs follow a uniform distribution, job sizes follow a uniform distribution, that means that I should use policies that try to process the job that's already there. Because if I have a job that's been processing for a certain amount of time versus a fresh job, well, I expect the remaining processing time of this to be less than a fresh job's expected processing time. So if job sizes are uniformly distributed, I want to use things like first come, first serve, or non-preemptive policies. What happens when we throw the exponential distribution in here? Let's take a look at that. Okay. Well, so if x is randomly distributed following exponential distribution with rate lambda, what is h of t? Well, what's the CDF and what's the PDF? Again, trying to do it off the top of my head. I should know this one. I hope I know this one. I get 1 minus the CDF, which is 1 minus. Do some algebra here. I tried to make the equal sign look a little bit better. Still looks pretty terrible. This board here, it wobbles. It's a wobbler, so you gotta watch out for it. Whoa, it's really wobbling. Gotta keep those boards in line. Okay. Well, this equals lambda. You should have a strong intuition for this, because we know that the exponential distribution is memoryless, meaning it shouldn't matter how much processing time we put into it, the processing rate remains lambda. And that's exactly what we find. Doesn't matter how much previous processing time you put into it, or if it's completely fresh, the processing rate of an exponentially distributed random variable is always going to be lambda. So let's go back to our initial question. Is it IHR, DHR, neither, or both? Well, is this thing increasing in t? No. Is it decreasing in t? No. That means it's neither of those? Wrong. Why? Because all we have to worry about for it to be IHR is it's non-decreasing in t. This certainly is non-decreasing in t, and in fact, it's also non-increasing in t. Meaning what? The exponential distribution is IHR and DHR. In fact, it's the only distribution, only continuous distribution with that quality. Okay, so with exponential service times, what does that mean? Well, we kind of already knew this, right? We have the question, should I interrupt the job that's being served, or should I let it finish processing and leave the fresh one to process later? Well, it's both, so it doesn't matter what you do. And remember, I put that one theorem up at the beginning, or factoid, I guess you could call it, at the beginning of this lecture, so like in part 1, and it said, hey, look, no matter what service discipline you do, if it's an MM1Q, meaning if it's exponentially distributed service times, it makes no difference. And that's exactly what we see here. It doesn't matter what you do with the exponential distribution, you're going to have exact or equal results. Okay, so we have IHR, we have something that's IHR and DHR. Are there any distributions out there that are DHR? Yeah, of course there are some. But there's one I want to focus in on. Pareto distribution. So I don't know if you guys have seen the Pareto distribution before, but it's one of those distributions that I really do feel should be taught more and more of in university. Because I think you do all your stats courses and you learn central limit theorem, all these Z tables, and you get like used to these Gaussian things and normal distributions and whatnot. And you get this strong sense that, loosely speaking, the world follows a normal distribution in some sense. And of course, that's more of a philosophical statement than a statistical statement. And I get where you're coming from. You look at certain things like, population heights, etc. And you're like, oh yes, a lot of the IQs, a lot of these things are normally distributed. Normal distribution is a nice distribution to explain what's going on in the world. And that's true for some aspects, for sure. But in general, and I mean, people would debate me on this, of course. This sucker right here, if you know one distribution to explain the world, this is it. So what is this distribution? Well, you can just Wikipedia the CDF and the PDF of it, but it has these weird qualities. And let me just give you a few of them. Just so you understand what the Pareto distribution is. And it has a few parameters, and it has like this alpha or shape parameter. And if we let alpha equal 1, we get this. So if jobs are Pareto distributed with alpha equals 1, of all jobs, which currently have size 1 second. We'll say at least 1 second. Half will have size at least 2 seconds. Half will have size at least 2 seconds. Okay, and I can extend that to a more general. If, you know, x is larger than t, then the probability that x is larger than 2t, so given x is larger than t, the probability that x is greater than 2t equals 0.5, and that's if alpha equals 1. So what's the main consequence of this? Well, the main consequence is if x is big, I expect it to be bigger. What do I mean by that? Well, the bigger x gets, the bigger I expect it to get. And it's a simple concept, but it's weird for people to think about. And it kind of goes against the grain. Like you look at the typical bus, waiting for a bus example, and you know, maybe a layman's, and maybe it is correct, but you think, okay, if I've waited 10 minutes, I expect now to wait less time. Well, maybe you should expect to wait more time. If you've waited 10 minutes, now maybe you should expect to wait an hour. And I mean, this Pareto distribution, like I said, it's a good one to know. Why is it a good one to know? Well, for this course specifically, you know, we talked about the MM1Q. Poisson arrivals, pretty good assumption. Exponential service times, a bad assumption. Well, if job sizes, they aren't distributed following an exponential distribution, how are they distributed most of the time? Pareto distribution. So job sizes, this is a very good fit. The Pareto distribution is an extremely good fit for job sizes. Well, okay, that means the longer a job's process, the longer I expect it to be. But I mean, I'm debating like what order to tell you guys all this. But the Pareto distribution, I mean, it turns out is a very good fit for job sizes, but it's a very good fit for a ton of things. So when it was originally, so I guess I could write applications or whatever. It was originally discovered by an Italian economist, you know, with the last name Pareto, and wealth distribution is the typical example. Distribution of wealth among citizens follows a Pareto distribution. Populations in towns and cities follow a Pareto distribution. Earthquake magnitudes. Follow a Pareto distribution. What else? I mean, just off the top of my head, moon craters. Is it OR or ER for craters? Whatever. Moon craters. The size of moon craters is a Pareto distribution. And similar or related to that anyway, meteorite sizes follow a Pareto distribution. And it goes on and on. Those are just the ones off the top of my head, but a lot of computer applications as well. File sizes across the internet, also Pareto distributed. There's like a bunch of other ones. Just Google like, you know, Pareto distribution applications and you'll find a lot of these things. So if you've ever heard, stock prices or stock shares and stuff like that, people that own certain like stocks, I believe it is, but you'll see, or maybe I've heard of this 20-80 rule or 80-20 rule. And it comes up all over the place in business. The most typical one is, 80% of your profits come from 20% of your customers, or 80% of the work in your company is done by 20% of your employees. And these are very, very, very good rules of thumb. It turns out it's true, and there's a lot of research that goes into it. But the 80-20 rule comes from the Pareto distribution. So essentially, 80% of the outcome comes from 20% of the sample size. And people know the 80-20 rule, and they talk about the 80-20 rule a lot, but with Pareto distributions, based off these shape parameters and the other parameters in the distribution, it can be a lot more skewed than this. Potentially, you could have maybe a 199 rule, meaning 99% of the work is generated by 1% of whatever sample size you're dealing with. For instance, I don't have any empirical data to back this up, but if I were to think about, if I look at every student in my class and I think, okay, how much time do I spend with individual students? Most of the students there, I don't spend a lot of time with. In fact, I probably spend 0 time with the majority of my students. They don't come to see me in my office hours, they don't ask questions, etc. But there's a small subset of those students I spend almost all of my time with, right? I might have a 20-80 rule or a 90-10 rule or whatever. And this comes up everywhere. And you get this notion of, they call it in the textbook, elephants and mice. And the idea is, a small, very small, potentially, sample of these distributions account for the vast majority of the behavior. So here's another comment here. So based off of, empirical data on job sizes and a lot of, I forget what it is exactly. You can check the textbook where the data comes from, but you get this result where 50% of the load comes from 1% of the jobs. What? So, you have jobs arriving to your system. It could be a single queue, could be a data center. Most of the time it's running smoothly, and most of the jobs there are pretty small, but all of a sudden you get this giant that shows up. And that giant job is actually responsible for 50% of the load. So the behavior you see from these systems comes from a very small subset of the jobs. If you don't want to talk about job sizes, let's talk about meteorites for a little bit. So think about that. The vast majority of meteorites that hit the Earth, how many things do they kill? Well, you think meteorite, maybe it's the size of my fist, comes down, maybe it hits the mud, maybe it doesn't kill anything. Maybe it hits a tree, kills a tree, hits a bird or something, I don't know, kills a bird. I'm sure some people die from meteorites every year. But the majority of meteorites, either don't kill anything or kill very few things, like grass, whatever. But every once in a while, every so many millions of years, a giant meteorite shows up and kills a ton of things. So I'm no paleontologist, but pretty generally accepted that at some point in the past, a meteorite hit Earth and killed 85% of life or something like that. So a very small subset of the meteorites impacted a very large portion of what those meteorites are actually doing. Most meteorites don't do anything. Most small jobs don't do anything to your system. Huge meteorites can cause a catastrophe. Large jobs can cause a catastrophe. And I'm kind of just going on a rant here. I'm kind of losing my train of thought. But this Pareto distribution, it accounts for so much. So not only are meteorite sizes Pareto distributed, but length of time between these catastrophic events is also Pareto distributed. Same with the earthquakes. So you think, well, if I were to look at time between certain mass events, like extinction level events. Like, there's some that are short in the beginning of the Earth's lifespan where there's volcanoes and all this other stuff going on. And now we're in a time where, one of these catastrophic events hasn't happened for a long, long time now. And you talk to some people, and when they're ignorant about how like these distributions work, they're like, man, we haven't had like a volcano go off and kill, half the planet in like 100 million years. Man, we're due for a catastrophe. Well, not really, because the time, I've put in 100 million years of processing time into this random variable. I expect that to be longer, not shorter. It's not the fact that, okay, man, we're coming up on that extinction event. We need to, be careful because we're due for that massive earthquake or we're due for that massive meteorite. Not the case necessarily. I mean, like, there is a probability that during me talking right now, a meteorite comes through my window, smacks me in the head, and you don't have to write the exam. But chances are more likely that I'm going to live my life just fine without a meteorite or a massive meteorite coming and blowing up the Earth. So, what else do I have to say about this Pareto distribution? I would encourage you guys to do your own research on it. It is a fascinating distribution with like a bunch of fascinating applications. I guess the bottom line application here, and I think I even forgot to mention it. Pareto is DFR, meaning the more time I put into a random variable that's Pareto distributed, the lower and lower the rate gets, meaning the longer and longer the remaining expected value of that random variable gets. So I just told you job sizes are usually Pareto distributed. Well, if I'm running like an MG1 queue and jobs are following like a Pareto distribution on service time distribution, does it make sense to do something like first come, first serve? No. You want to preempt these things. Because if you do something first come, first serve, and one of these massive jobs arrives, what happens? Well, you get a massive job arriving that, takes up the entire like system for a long, long time. You get all these smaller jobs arriving behind it, and they get stuck. They have to wait for this entire large job to finish before they get processed. And in fact, you can look up the actual values of this, but basically, if I'm pretty sure, I can't remember if it's strictly less than 2 or less than or equal to 2, but if alpha is, less than 2 for sure, the variance is infinite. What? I didn't even know you could have infinite variance. Yeah, you can. You can have infinite mean too. In fact, if alpha is less than 1, the mean of this distribution is infinite. Well, hold up. If the variance is infinite, what's the theoretical expected response time of my MG1Q? It's infinity. Ouch. But if you use something like processor sharing, preemptive last come, first serve, least attained service, or non-blind policies like shortest remaining processing time, you can avoid some terrible, terrible, terrible performance. So anyways, like I said, I kind of went off on a rant there, but that can be fun sometimes. So I probably had some other things I wanted to say, but I can't remember what they are. Anyways, check out Piazza, ask some questions. I'll make some tutorial videos where we can discuss a little bit more of these things potentially, or just do some problems. Check out the assignment. I ask you guys just to think about the Pareto distribution for a little bit. Come up with a real world example. You don't need to give me, of course, like empirical data and do like best fit and all that stuff. Just give me like, a rationale of, I actually think, blah, 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 or I don't know, don't use this example, but like maybe like a length of song times or something, right? Could be Pareto distributed, or length of movies, or I don't know, heights of trees. Those probably aren't Pareto distributed, but just, think about it. And then based off what we've said here, do a little bit of research and come up with a justification for why you do think it's Pareto distributed. Don't need anything formal, just like maybe 1 or 2 sentences about your personal experience with those things. Anyways, thank you very much for your attention. That's the end of the course. I hope you learned a thing or two. Hope you had a little bit of fun. Good luck on the exam.